guys a question. Whenever we see this problem, right, there's a simple cantilever beam formula, right? So we all are familiar with the formula, correct? It's called the cantilever beam. And this is what we expect to use to be able to calculate the deflection in this beam, right? And so, but if I were to ask someone in, say, Japan, how they would solve this, wouldn't you expect them to use the same equation, correct? And so why do we use this equation? Because it's basically, used and proven through the years and things like that, right? And so that's why we depend on it. So basically, this is a formula that we use for this application. And is it a language that's known worldwide? And it is. It's a common language, right? Because as engineers, we use formulas to figure out problems and things like that. So how about this, though? This is a landing gear of Boeing 777. What formula was used to design this mechanism? So currently, remember, this is please respond. Just ask questions anytime. But currently, if you were given this problem, how would you start to solve a problem like this? Anyone? What would be a common thing to say? Why did you design this way? What do you think the common answer would be?
Because it's always been done this way.
Okay, that's one. What are some other ones?
Looking at 4-bar linkages.
Okay, with four bar linkages, very good. Anything else? I mean, if you're a mechanical engineer, right, and then somebody comes up and says, why was this mechanism designed the way it was? And why did we use a revolute joint here? Why did we use a spherical or universal? How would you answer something like that?
To meet the motion and durability needs.
Okay, sure. And then maybe sometimes somebody made a prototype, maybe, right, out of it, and they build it from the prototype. But I'm looking for like a formula, just like we did for the cantilever beam. What currently do we as mechanical engineers have in our toolbox that can help us solve the degrees of freedom for this mechanism?
Gruebler's count.
I knew you were going to say that. Yeah, but yeah, before that, I didn't know that either, right? So I kind of just stumbled on it. So basically, Gruber's formula is the formula that I'm going to introduce you. Like, for example, if you see a helicopter rotor, the reason why I like to choose a helicopter rotor is the most complicated and controllable mechanism that actually flies. So if Gruber's count works on this mechanism, then it should work on every mechanism. Okay, so, and obviously we want it to be a common language just around the world, just like the cantilever beam. Okay, so for example, this is what it will look like. I can describe for you in one page what the mechanism is capable of in one page. And there's basically 132 degrees of freedom. And you end up with all the joints that you apply, you end up having 5 degrees of freedom. Okay, so that's based on that one formula at the top. Okay, so this is just like the big picture. And it is a worldwide language if you learn it. Now, Gruebler's, I didn't know about this until I worked at a company where we simulated multi-dynamic problems. It's called the Atom software at a company called MDI back in 1995. But it originated from Germany and also Russian scientists back in 1883. But the question is the mobility formula, and why is it not used? I was never taught this in school, and I didn't learn this until later. So what I found out was that there could be some problems with it if you use it incorrectly. But there's a company that I was telling you about, it's called Mechanical Dynamics Incorporated, and that's what I used to work for, and they figured out how to use it correctly, and also it's a precursor to set up their models before they run it in their multi-body dynamic software. So I'm going to play a video showing what I did in the company, and we'll discuss it afterwards. Okay, so please let me know if you can see and hear it. Okay. Okay, guys, can you guys hear it? Can you guys hear it? And see it?
I can hear it.
Okay, good. I'll explain. So at the time that we were doing some work, trying to propose a software to the Joint Strike Fighter program, and I got a chance to model all of this geometry from scratch and use the Atom software to do drop tests and things like that on it. But before you actually put it through the solver, you had to do what we call Gruebler'S count to make sure you get the right inputs and outputs desired. Here it is doing drop test. Here's the input. You see the difference is amplitude. So it bounces. And also one up the table is actually run looks like a project and you go to predict also good. Yeah, Brandon had a Honda ATV put it in marketing, but yeah, those right highlight messages too. Yeah, of course it is marketing.
Hey, Lane. The music's kind of drowning out your voice a little bit.
Okay, sorry. Can you hear me now?
That didn't change the audio on this side.
There. Can you hear me now?
Yes.
Okay, so basically what it is Ford, GM, or Chrysler, they use the software to do their multi-body dynamics on their suspension work and things like that. So that's what I did there. And then these are the companies that actually use the Atom software. As you can see, the Boeing aircraft companies. Messier Dowdy. Does anyone know what this company does, out of curiosity? Messier Dowdy, they design and build the majority of landing gears for all the aircrafts around the world, military and civilian. And NASA actually used it for the Pathfinder project also. So that's how I heard of it, right? And I was trying to say, well, if I know about this, why can't we just share it with other people? And the company shared the software, but they weren't able to share it in the way that I want to share it, where you don't really need the computer to figure out how to do Gruebler'S count. So in this situation here, before I go on to it, I just want to show you the advantages of using Gruebler'S count. Number one, it would be a common math-based language when you do mechanism design, and it would be worldwide. You know, if you learn the Gruebler'S language. Number two, it will ensure that your mechanism won't bind even when it flexes. Even though you ever heard of the term multi-body dynamics or rigid body dynamics, and they usually think of Gruebler'S count, but it's a misnomer. Using Gruebler'S count will give you the ability to have the mechanism run even if the part flexes and even if the temperature changes, things like that. So that's the power of Gruebler'S. And it'll make your mechanisms line up themselves. You know, it will make it smart like a thermos. You know, like for example, you put hot stuff in the thermos, it stays hot. Put cold stuff in the thermos, it stays cold. So how does it know? It just knows. As smart as the thermos. It's just like your mechanism when you design it. And then also reduce premature joint wear, and you end up a very robust design. And Brian may ask me to put in get a pay raise. Okay, so this is just a small part of the presentation. There's going to be more stuff that's advantages for using Gruebler'S count. So here's basically what Gruebler'S count is. It's a subtraction problem. I've never had a formula where all you need to know is addition, subtraction, and multiplication. So it starts with this. System degrees of freedom is your system, your mechanism. And then all the number of moving parts that's in your mechanism, you multiply by 6 degrees of freedom per part, and then you subtract the joint constraint degrees of freedom, and you get basically 3 answers, right? So one of the answers is if you get a 0, that means the mechanism is fully constrained. If you get a positive 1 or more, that means you have freedom of movement in your mechanism. And if you have -1 or less than -1, then your parts are over-constrained, there's stress, and your mechanism will bind. So let's look at real quick what Gruebler'S count starts off with is we are familiar with the degrees of freedom, right? So each object in space can translate in XYZ, and it can rotate in XYZ. So 3 + 3 is 6. That's for one moving part. So let's go through the basics of all the joints in the mechanism. So everybody recognizes the hinge joint. So basically, the part by itself is 6 degrees of freedom, but if you attach it to a hinge in this case and to ground, you subtract 5 off of that, then you have 1 degree of freedom in your system, right? So the 5 is an abbreviation. You'd like to use R, which represents revolute joint. So that has a 5 degree constraint degrees of freedom. And you've seen this prismatic slide. That's a P5 is a value of 5. Cylindrical is a value of 4. These are the typical mechanisms joints you see. Universal has 4. Spherical joint has 3. A planar joint, I was trying to find one in reality. There's a pump that rotates this plate, and that's a sliding plane-to-plane surface. And this is an inline. Basically, it's a ball joint with a square peg going through it, you know. So that's an inline joint. And then, of course, we have like an in-plane joint, which is similar to a ball inside a slide that keeps it from going up and down. And these are basically the joint symbols that I'll be sharing with you guys. So there's revolute, and so these are the constraint degrees of freedom. Okay. All right, so let's start with something basic here, right? Everybody knows a door, correct? We use it every day. Well, a door is basically the simplest mechanism that we have. So it's one door, one body moving back and forth on a hinge. Well, one door, the way I separated in the calculator here, the yellow is basically the moving part, and the blue here, the light blue, is basically the number of joints you put inside your mechanism. So in this case, I just put the door here, which is one moving part, times 6, you have 6 degrees of freedom. All right, and then that's moving parts of degrees of freedom. And then you add a hinge to it, which ties to the ground, which has a value of 5. So 6 subtract 5 is 1. And that means you have the middle line here is positive 1 or more. That means it's partially constrained. That's what you want. You want your door to swing back and forth. But if you look at your door, though, it isn't just one hinge, is it? It's usually 2 or 3 hinges. And that's why you hear doors creak all the time once in a while, like the temperature changes, things like that. Well, why is that? Let's take a look. Well, we still have one moving door, and then we actually have 3 hinges now. So that's one on top, middle, and bottom. So let's do the math. So since you have 3 hinges, now you got 3 times 5 is 15. So 6 subtract 15 is -9. So basically, it's really over-constrained, and parts are gonna creak, and then they're under stress. That's why you hear it when the temperature changes. That's why you hear it creak sometimes in the winter or not, you know. So why is this? The door creaks all the time. I have a situation in my house where the door actually creaks, you know, and I said, well, is there a way for me to use Gruebler'S to fix my door, right? So I want the answer to be system degrees of freedom of 1. So I said, well, let's play with the joints. I can't use a revolute joint. That's too high of a value. So well, let's use a spherical joint at the top here. And at the bottom, I use a spherical joint that's on a slider. So it's similar to the inline 2, right? So now you got 6 subtract 3 subtract 2, which is equal to 1. And then here's a video of me actually making this for the door that creaked. So it's a short video here. Here we go. All right, so here we go. Really think about it. Look at all these powder marks. That's basically the hinge wearing out. Okay, here we go. That is awesome. Okay, so I don't need the middle part, right? So I remove the center hinge, and then I'll speed this up a little bit here. And so I basically drill holes into the door so I can put in those ball joints. And then here's what it looks like at the top. it's an S3 joint, so basically it's a ball joint. At the bottom is a S3 that slides up and down if the temperature changes, and then it will accommodate for that. And then here's what the door sounds like.
Okay, now it's fixed.
All right, here we go. So basically that door I haven't touched ever since I fixed it. So it will never creak because under flex, the balls will line themselves up. Even if when you mount it incorrectly, it'll still work. So that's the power of Gruebler's just for a simple hinge joint. Okay, let's move on to a mechanism that has two moving parts. Well, one of my favorite landing gears, which I made, can you guys see this on the screen?
Yes.
Okay, this is the Concorde landing gear, and what they did was to keep it from that's what they call the forward backstay, the drag brace. And when they assembled this strut and the drag brace, they don't bolt it together, they use joints. So basically the math is this is the vertical strut and it has a revolute joint here, and then here it has a universal joint, and down here is a spherical joint. Well, actually I just made a spherical joint because it can actually rotate, but just stay with me here. So with the math, there's actually two moving parts. There's a strut here and there's a drag brace, right? So take a look at the math. That's two moving parts. So 6 plus 6 is 12. And the joints it put on it is a revolute joint, which is 1, which is value 5. A universal joint is value 4, and a spherical is about value 3. So 12 subtract 12 is 0. So 0 doesn't mean it's bad, but that means it's fully constrained, and that's what you want, right? You don't want the landing to be stressed when it's when it's flying in the air and when it's taking a load. You want it to just be set where it's at. So really think about it, this triangle is like a perfect triangle. There's really no slop in it because, well, it depends on the slop you have in your joints alone, but it's a perfect situation. So that's why Gruebler's is really good for too. It's also good for static. So when the temperature changes, when the strut length changes, it'll accommodate, right? Let's say it's stretched really long. Well, what happens then? If this stretches, then it's going to move to the left, right? Things like that. So that's the power of Gruebler's, not just as mechanism, but also in statics. And of course, another way that we use Gruebler's is in a robotic arm, which is kind of boring, right? Because you got two moving parts. You got two revolutes. Well, it's not tied back to ground, so you have 12 subtract 10. That's two motions that the system needs. So basically, you kind of see the ramp up here. So Gruebler's is used so that you can figure out if your system is binding or not according to the subtraction problem here. So here I'll just go through a simple mechanism for your double wishbone suspension here and show you some practicals. All right, so in a regular wishbone suspension, the tires here is basically a parallelogram, right? And so they're basically, even though they call 4-bar, it's actually 3 bars that are moving, right? So that's what the calculator just cares about. So if I made a mock-up of what's on the screen here without the tire, right? So this is all 5 revolute joints, but you notice they're not parallel with each other. I did this on purpose that they're at different angles. You notice it doesn't even fall down because it's fighting itself, right? And so, but look, it's actually moving, right? It does flex, but then that's kind of false positive because the plastic parts are flexing. So let's put it to the test. Okay, so let's take a look. Right now, they're basically 3 moving parts. You got the upper control arm, the UCA, the axle, and the lower control arm, the LCA. So that's 3 moving parts. 3 times 6 is 18. Now let's look at the amount of joints we have. We have 4 revolute joints, which is value 5. So you got 5 times 4 is 20. So you got 18, subtract 20 is -2. So -2, that means it's binding. It's gonna, it's over constrained. So if you use it continually, it's because something's gonna wear and some parts are gonna break through time. So that's how you figure out it works or not, even though it's a false positive. So let's try to fix this mechanism there, right? Let's try to fix it. So we wanted the answer to be 1 because we wanted to rotate up and down freely, regardless of the angles that these revolute joints are at. Okay, so let's play with the numbers. Let's go to the next version here. Oh, before we do that, one of the things I wanted to let you know is that one of the main reasons why Gruebler's count has not been used through the years, and you don't really hear about it, because they're missing two secret items, which I kind of stumbled upon through the years. For you to understand, to diagnose Gruebler's, is one of the misconceptions when people use the Gruebler's formula, they assume that all spin axes are parallel. And then they also assume that all distances between linkages and holes are the same. But then I realized, you know what, can we really line up two axes parallel with each other? I mean, just like at the door, right? You have those three hinges. It's like impossible. If you ever hung a door, it's really trying to get this lined up, and then you need to have like a smaller pin to make sure the slot fits and things like that. So that's rule number one. You have to assume that there's no axes that are ever parallel. That's rule number one. Rule number two, that no distances are ever equal. And if you guys remember GD&T, this is what we try to focus on minimizing, is the angle between parts that, you know, holes and things like that, and also the distance between them. But you have to remember these two, because once I found out I can apply these two rules, then the formula works 100% of the time. And that's why I wrote a book. That's why I made a website. I created like 60 mechanisms, and they all work 100% if you remember these two rules. It's very important, because with that, that's how you can diagnose problems. Like for example here, so assuming that since I made the model, all the axes are never parallel, then you already know that they're going to be binding anyways, right? Of course, when you build it, you want to make it as parallel as you can, but in math-wise, it will never be parallel. So that's very important. Okay, so let's try to fix this now. So I replaced the top bar with, instead of two R5s, I went to a ball joint, which is an S3, a universal joint. And then if you do the math, over here now we have two revolute joints now down here, which is equal to 10. You have one universal, which is equal to 4, and one spherical, which is equal to 3. So that's 17. 18 subtract 17 is 1, and it works fine. So here it is. I built it as it is. Up here is a universal joint. I mean, a spherical joint here. You see the ball, and this is universal joint right here, and it works fine. Okay, so let's go to the next one. And by the way, this is a sample of a mechanism that's used on the, what is it, the Mustang car. Down here you see is a R5 revolute joint, spherical joint here. But they actually have a spherical joint here too, which is an extra degree of freedom, which can spin on its axis, but it's basically the same thing. All right, here's another one. One thing that's nice about Gruebler's count, you can actually substitute parts, where a universal joint is basically U4, but in reality, you actually have an extra part with two revolute joints. So if you look at here, if you look at this universal joint here, there's one axis here and one axis there. All right. So basically, this is like the second part, which I call a link. Right. So let's do it. So now we have an extra part in there. It's called a link. Now we have 24 degrees of freedom. All right, so now let's redo the math. So how many revolute joints do we have now? We got 1, 2, 3, 4. So 5 times 4 is 20. And you still have the ball joint at the end, which is right here, which is 3. So 24 subtract 23 is still a value of 1. So you arrive at the same answer even if you use an idealized joint or the actual joints themselves. Okay. All right, let's go to the next one. So let's say I wanted to be able to steer my wheel. In this case, I want this axis to be able to spin. So how do I do that? Well, as you play with the joints, you keep the inner ones as revolute joints and the outer one as spherical joints. So let's do the numbers. Now we're back to 3 parts again. So it's 18 degrees of freedom. I have 2 revolute joints, which is 10. I have 2 sphericals, which is 16. So 18 subtract 16 is 2. So there's 2 degrees of freedom. So here's what it looks like. Well, 1 degree of freedom is up and down, the rotation here. But the 2nd degree of freedom, since there's 2 spherical balls, it will pivot around there. So now you have a mechanism that can suspend up and down and rotate, right? And one thing that's nice about this mechanism is that you can handle torques better in this direction because it's spanned between the two discs here. Whereas the other one, the torque is taken up just by the lower arm alone, whereas the top one is going following the direction, right? So those are two differences. Okay, so now one last thing. Let's say I want to be able to steer this thing now. I want to have, not steer, but to keep it from rotating, since I have the advantage of putting a lot of torque through the mechanism. So let's go to the next one. Then what I'll do is I'll add a steering link basically, but I'll fix it to keep it from sliding. So now I added another part. So look at here, now we have 24 degrees of freedom. If we do the math again, we end up having 2 degrees of freedom. Since the bottom link has 2 spherical joints there. So here it is, the mechanism here, and then the 1 degree of freedom, it rotates up and down. The second one is in this axis here. This can actually rotate, right? This link can actually rotate because it's between 2 balls, just like the door hinge, right? So that's what the formula gives us. So do you guys have any questions so far on what I've gone over?
No.
Okay, sounds good. All right, so one of the things that I ran through is since I've learned how to use Gruebler'S, I figured out how machines should work. So I see excavators, you know, on highways all the time, and there's hydraulic cylinders that move the arms and things like that. So I always wonder, you know, those hydraulic cylinders, they should have either a universal joint at the end of the cylinder or a ball joint at one end, right? And so that should be the way you do you know, the joints and things like that. But then I found out they actually have pin joints in both ends. So the cylinder has was an R5. This is the before. I'm saying over here I'm talking about, because there's a major company, I won't say the name, but they used to do it this way, which they originally used ball joints on the ends of them. And doing the Gruebler'S count, you get 3 degrees of freedom, and which is good. That actually worked well, where the rod can slide in and out, and since there's 2 spherical joints, the rod can spin on its axis, and also the cylinder can spin on its axis. Even though you have extra degrees of freedom, it still works fine, even if parts are bending and things like that. But then the next series, they decided to go back and change the spherical joint to a hinge joint in the front and change it to the back. So they went from a 3 degrees of freedom mechanism to a -1. And so I said, I finally got a hold of the engineer. I said, why do you guys do that? Because before you used to have ball joints at the end of these cylinders. He says, Lay, you're an engineer, right? I said, yeah. I said, but I said, didn't you put, you know, more constraints back in and you made it bind by putting the pin joints in? He says, Lay, a spherical joint, a ball joint is like $80. But a pin joint is only $10, and we wanted spare parts. So that was his answer. That was their business strategy, is getting spare parts. So the customer doesn't know any better, right? But as you and I, as engineers, we will know that, hey, no, that's wrong. You shouldn't be selling me that stuff, you know. But the customers, they don't know any better, so they just bought on, and they figured, well, they got to replace those pins and rods and cylinders more often because of that. So that's one thing you need to be aware of as an engineer. You gotta make sure you understand your mechanism. Don't just copy it from one person to the next, you know. And where I work right now, there's one of the most common Gruebler'S violations is how they use air cylinders. You know, when you buy an air cylinder, it's usually a revolute joint on the end, and then you got a rod that's threaded, so everybody puts like a ball joint on the end, right? So, and then when they install it this way, well, remember there is a revolute joint here and a revolute joint here. Now you remember the Gruebler'S count rule, no spin axes are ever parallel. So if you have 2 revolute joints, you got to start paying attention. Well, this axis here, as it's moving the arm, is never going to be parallel with this. So let's say you were able to install it this way, and if you do the math and use the right joints here, you have an S3, which is a ball joint, a C4, which is a cylindrical joint, and R5, and there's 2 of them. Now you get 18 subtract 17 is equal to 1. You would say, oh, well, this mechanism is free to rotate and it's not binding, right? But that's where people make a mistake. They say, well, this should work fine, but actually you have to remember these two rules. So the rule that applies here is no spin axis are ever parallel. So if you really think about it, let's say this revolute axis is 35 degrees off. So let's say you were able to install that way, but the moment this slides, it's going to bind, right? So at rest, let's say we're able to assemble this way, the 1 degree of freedom is basically the rod being able to spin on its axis, because the C4 is a cylindrical joint. It can slide and rotate, and the ball joint is on the end of it. So basically, what's really sliding here, moving here, is the rotation of the rod, right? But I would have known that if I didn't apply this rule, right? So that is a common misconception. And so the way you fix this is you want to let the C4, the cylindrical joint, let it spin and rotate. So you put a universal joint in this end. So you do the math again, then you get a degree of freedom of 2. So that means this can slide and this can rotate at the same time, right? Again, using these two rules. And this is what I did when I was working on the Avatar ride. I was fortunate enough to design the mechanisms that go underneath the Flight of Passage ride at Disney here. And there's 3 air cylinders that are used for the mechanisms that lock you into your seat. There's a seat that comes up on your back. And there's a total of basically 192 riders, but there's 3 cylinders per rider. So it's 576 air cylinders that are used, day in, day out. And every year there's basically 8 million cycles on this cylinder. And at last check, it ran for 2 years without any cylinder changes. And that's 16 million cycles on an air cylinder. That's huge. Why? Because it works because of Gruebler'S count. This is what I use, and it works because there's freedom for the mechanism as it bends, and it'll self-align itself, and it reduces the wear. So that was my big success story there with Disney. Another most popular Gruebler'S violation is when people do slide tables, and we do that as our work too. It's basically a slide table. They use these prismatic slides like a THK rail or whatever, and you have to line them up really specially. And then when there's line distances, it will bind up or wear and things like that. And so here's the reason why. So basically, you have a mechanism that has this one table that slides back and forth, but then you get all these constraints on it. So you got 4 prismatic joints, which has a value of 5. So 6 subtract 20 is -14. So that's just horrible, right? So that's why they won't last very long when things flex. So in my book, I actually showed how to fix it, right? So if you instead of using 4 of them, just use 3 of them, and they have a sway link, and then have ball joints at either one of those ends. And so basically, the table is it's resting on 2 ball joints and a revolute joint. So what this affords you is if things are bending or misaligned, the table will move and twist accordingly. And that's why you get 1 degree of freedom. And another way to do it too is on my website is another example. It's a cheap way of doing a slide table, and I'll show you why. So you notice this rod right here? See, I just moved it to the side and it still works because there's a sway link. Yeah. Move to the other side, it still works too. Now, obviously, when you mount it, you don't want it to be that angled off, but that's what Gruebler'S affords you to do. You know your mechanism, and you can decide what tolerance you have on that. Now, does anyone know the tolerances that is required for a THK rail between the parallelism? Does anybody know that? What are they asking for? Do you guys remember?
I used to design slide tables just like this, and you're exactly right. They would get into to a bind, so the technician we'd have to put enough tolerance in the bolt pattern to make sure everything was parallel and tested. Right.
And they were asking like thousands, within distance one another and parallelism and everything. And after a while, when things bend and wear, it's going to get out of place too. So one thing is nice about learning how to do it this way, you decide the tolerance of your mechanism. let's say I can only keep it within plus or minus 5 degrees. Well, this mechanism, as long as you make the sway bar long enough, it'll find its center, right? It will decide, it will never bind, right? So that's the power of Gruebler's count. All right, let's go to the next one. So I have a success story here. I say that Gruebler's count relieves carpal tunnel. Well, I have a sister, she's a pharmacist, and I visited her last month, and she says, Lay, you know, these medicine bottles, I have to open, you know, they have to push down and twist. I have to open like 400 of them a day. I've been doing that for about 10 years, and now I end up getting carpal tunnel. Says, Lay, can you do something for me? Can you make a mechanism, a machine that would do this for me? And I said, let me get back with you. So about 3 weeks later, I mailed her this mechanism, and I'll show it to you. So here it is. What this mechanism does is there's a motor at the top, it has some rubber, and then I put the medicine bottle and use the lever arm to push it up into the spinning motor, and that just opens it up. And the mechanism I use, I want to make sure this was light so she can be portable and carry it to her pharmacy. So I use Gruebler's on this. Basically, these are hollow brass tubes. I have a hollow tube sleeve that goes out, and I want us to be able to be accurate to slice up and down. So you have one moving part, which is 6 degrees of freedom. I have a cylindrical joint, which is a value of 4. And over here, I have what you call an end plane joint. It's basically, it's like a fork that goes around a rod. It's like similar to, so it keeps it from rotating basically. And that's all it needed. And this slides up and down all day, 400 bottles a day. It's been running great, you know? And so that's because of Gruebler's count. So as you can see here, this is the math I used. I didn't include the lever arm, but that was she was really happy with it. So Gruebler's count relieves carpal tunnel. All right, so let's look at the finale here. So these are the biggest advantages of using Gruebler's count. Number one is a common language. So you can talk to anyone around the world because it's based on math. And another one is as smart as a thermos, right? Because it becomes smart, just like that parallel table that I was telling, the slide table. It just knows because you decided to put the right joints so that it will accommodate the changes in installation or changes in slop and things like that, you know? So that's very powerful. So the mechanism, once you build it, just like my door, I want to design, build it, and be done with it. Just like the machine I did for my sister, I do it once and I don't want to touch it again. It should work forever, right? Now, obviously, things can wear if the slide tubes wear, put oil on it, but pretty much it's going to last forever. So that means you also have a robust design. And then another advantage too is that in FVA, by the way, you get correct values. You won't be overstressed. And again, with the slide table, you decide the tolerance. So THK comes to you and said, it's got to be within this parallelism. I said, bag it. I'll decide what I want to do with your THK rail. I'll put some joints on it. I'll make it 10 degrees off and it'll still work, right? So that's the power of Gruebler's count. And then not only that, now you have a formula in which you can check others' work. And the other people can check your work as well. So it basically levels the playing field because it's based on math. And then one of the very important things is you can defend your designs in court. You won't have to say, somebody else, I copied somebody else's design. But the problem is when you copy somebody else's design, you could be copying their mistakes and not know it, right? Or you could be that the excavator company. We made it wrong on purpose so we can get more spare parts. When you try to do that with Universal Studios and Disney, you'd be out of a job, right? And one of the things that was really interesting when I started doing theme park entertainment design about 2009, I believe. I'm not sure you guys know, there's a gentleman by the name of Mike Cadu, and he was the head of mechanical engineering at the time for Universal Studio Ride Systems. And he sat me down one time and said, Lay, whatever you do, I want you to make sure you keep good records of all your calculations, all your assumptions and things like that, because when you go to court, you can defend yourself. And that just woke me up like, wow. I really need to own my designs and know everything about it, right? Especially mechanism. Why did I design this way? Here's the reason why. Why was this revolute joint here? Because of this and that, right? So that gives you that backing, right? And then by the time you build a prototype, you know it'll work every single time. And when I made my website, I built all this mechanism, as you can see, and every time I designed it using Gruebler'S count, when I made it, it worked the first time. Didn't have to do anything. I used the right joints 100% of the time. All 60-something mechanisms I did. So I'm trying to prove out that this, if you use it with its 2 rules I was telling you about, it works 100% of the time. And then obviously, yeah, what does it do? It builds confidence in your customer. That's very important because you're giving them the right tools to check your work with, right? They know that there's no other tool that you can use to check your mechanisms besides Gruebler'S. And obviously it gives your young engineers more confidence too. And Gruebler'S count is also used in simulation software, just like I was telling you about the Atom software. And then Simula uses it, Altair uses it, and things like that, ANSYS. But the precursor, though, to using this software, you have to know Gruebler'S, right? Gruebler'S is, you have to design it using Gruebler'S or the software will give you wrong answers. And one of my crowning achievements after I left the designing for the theme park industry is I got Universal Studios to use Gruebler'S. At the time, I was working there with Brian Burns, and we did all these animated figures together using Gruebler'S count. And well, I don't know. Well, how many degrees of freedom do we have, Brian, in those animated figures we did? It's in the hundreds. I can't remember.
It was somewhere just above 100.
Above 100 some degrees of freedom, right? And then we knew how many system degrees of freedom we got back, you know, because we used the right joints. So every time we fed it to the solver, it gave us the correct answer. And then I taught this class to Universal Studio team, and they liked it so much that they ended up putting it into their animatronics requirements now. They said, if you do any animatronics work for Universal Studios, you have to verify the joints using Gruebler'S count or something similar, which is basically Gruebler'S. So
I think the timing is funny because I think one of the teams, some of the guys on here just got that request from Universal.
There you go.
So
Yep.
it's Lay's fault.
Yeah, it's my fault. Well, also the reason why I wrote the book is Tim Eck is the one at that time I taught it, and he was there. He's like, "Wow, Lay, why don't you write a book on it?" I said, okay, sure." So my book sold for what, $15.99, and don't worry, I'm not making too much money. I'm making only $2.23 per book. But since I put it on Amazon, it sold like 251 books so far since this November will be 2 years. I have a YouTube channel, which I was telling you about all those mechanisms. And then that's it. So I have time for questions and answers for 10 minutes. So fire away.
Hope you don't mean me.
Oh, I'm talking to you.
Hey, Lay, what's your website address?
Yeah, just type in Gruebler'S count, all one word, Gruebler'S count.
With the Gruebler count stuff, you're kind of reducing the number of like points of contact from like your loaded actuator to the structure around it. Do you ever see like increased structural loads that lead to premature failures due to that?
No, because one of the classes I wanted to teach is Brian's remember this. It's called S Mafia. It stands for Stop Spending Money on FEA. And basically, one of my hobbies is I design and build RC planes out of balsa wood, and you gotta make it light, right? And like landing gear attachments to the fuselage and things like that. So you learn about where to mount your cylinders, right? So especially like an aircraft structure, right? Anytime you mount something hard like a landing gear, things like that, you want to mount it to an intersection of 2 walls or 3 walls, right? Just like the corners of a triangle, right? So if you do that, then it will never fail, right? But the failure is when engineers fail to realize that, oh, this is going to be a point load. am I pushing onto a plate that's going to deflect, you know, or buckle? I have to make sure I put it to the apex of a triangle or something like that. So since I've done that, I haven't had any situations actually fail. Thank God for that so far. So what are the challenges you have when you guys design mechanisms? Do you guys generally just copy what you see and then you go on? How do you guys know your mechanism is going to bind or not currently?
I think currently, if SolidWorks allows you to do it without it being over constrained.
Okay, that's a good one. I found out that SolidWorks can fail in a situation. If you go to my, let me go onto the web here real quick, and I'll show you. There's a situation where the Gruebler'S is correct, but then SolidWorks is wrong. And then I actually built it to prove out Gruebler'S, and the physical model actually worked. So I'll show you here. Let's see, I'm sorry. Hold on. Go to the website. Okay, there's a mechanism called the Almond 90-degree drive. It's a noiseless drive. It was built back in the 1800s. I thought it was kind of neat, so I decided to build it and put Gruebler'S to the test. So can you guys see my screen? Guys see it?
Yep.
Yes, yeah, you're good.
Okay, so if you look at it here, it's translating, I'm turning this and it's rotating this, right? And so the original model had two spherical joints, but it had a round rod. No, there you go. It has a round rod that goes through this, right? And when I did the calculations on it, I said, well, it's extra degree of freedom, so that means it had two. So I said, well, after I figured out this can be an inline where it's just a square peg. And when I did that inside SolidWorks, it failed. It just didn't like it, you know? And then I did even another test where I actually rotated this angle here at 2 degrees instead of 90, and that failed too. But when I built it, it worked fine. So that was a situation where, remember, it's not using Gruebler'S when they use the CAD package. Remember, you can actually you can over constrain something in the CAD package and it'll still run, right? Like you put a face to face and you put a cylindrical joint or to that's perpendicular, and it still works for you, right? But in reality, it's violating Gruebler'S count. So this is one situation I found out that Gruebler'S count works all the time, and the CAD doesn't always work all the time. Another thing too I'd like to share with you is, do you guys see this little mechanism right here? Does anyone know what it is?
It's an oil pump rig.
Right. And as I'm running here, you can see this is like a ballast weight, and this is what it does all day, right? But they're not using the right joints, because if you don't mount these perfectly in line, because they have like revolute joints everywhere, and it can bind. So I said, well, let's fix it with Gruebler'S. So what I do is I did the Gruebler'S. I made this a spherical, this is spherical, and this is spherical. And what happens if you mount this a little bit off? You see that's off, right? But watch, it'll still run. Right, but just kind of wobble a little bit, but the system lines itself up because of Gruebler'S. You see that? So that one thing that's nice about Gruebler'S is when you don't have to worry about lining things up so perfectly, you know? You can use bolt hole tolerances and it works fine. And one of the things that Brian and I worked on it, we made Universal Studios' first animatronic hand. It was bigger than my hand. That's like a 6-foot figure. And I was using Gruebler'S on all the joints in there, and I didn't GD&T anything. I just used bolt hole tolerance, and it went together fine, and it worked great. Brian programmed it. It took like 2 people to put on the glove, right, Brian? And then it ran for about 2 million cycles or more, or whatever. And again, no GD&T needed because I was using the right ball joints and hinge joints and things like that. So that's the power of it. a powerful value added when you use Gruebler's count. When your maintenance guy comes in, if you design it right, you can get a high school student to torque down on your bearings. If you do it right, it will never bind. So that's the power of Gruebler's.
So I have a question about your backhoe example.
Oh wait, which example?
The backhoe example where it was a case backhoe where you said that
The backhoe, yes.
The pneumatic cylinder needed sphericals on both ends.
Yes.
So with a lot of our mechanisms here, we end up having to use anti-click-clacks because the cylinder wants to
rotate.
To rotate, yeah.
Yes.
So what can you add? What can we do besides having a non-rotating cylinder to alleviate that last degree of freedom that causes that click-clack?
Well, then that's where you put a universal joint in. So do you see this mechanism here?
Yes.
Okay, so what I did here, this is before 3D printing. I machined all this. This is a landing gear for a jet fighter, an A4. And to let it dampen for this model, I put an air cylinder here. So you look at the air cylinder, it has a spherical joint at the end here. And then since it's spherical and this rod, this actually rotates, right?
Right.
Inside sleep. But then down here, to keep the body from moving, I put a universal joint down here. And that is anti-click-clack. That prevents it from rotating. So that's how you do it. So the key to this, I was going to make a t-shirt for Gruebler's, like a 4-bar linkage, it would be like 5 plus 5 plus 4 plus 3 equals 1. So basically, when you have a 4-bar, you have 2 revolute joints, a ball joint, and a universal joint. That's how you get it to not bind. So in a cylinder, it's the same way. You have a 4 universal, right? And then a P5, you don't want to just rotate, that's a 5 value. And then a spherical here and a 5 here. So 5, 3, 4, 4. Wait, up to 5, 3, 5, 4. So again, this 5, 5, 3, 4. That's in my book. So if you have, but to answer your question, basically you put a universal joint, and that will prevent it from rotating. Yep.
Thank you.
Yeah, no problem.
And
back
to the example about the ball table with the 2 THK rails.
Yes.
I used to have to troubleshoot those when they were binding, and I almost always found out that the planar surface that the rails mounted to weren't parallel to each other, and they almost always bound up. And basically, like you said, the tolerancing of the components, I would have to chase the tolerances until I found, that it was either wasn't parallel or perpendicular to each other in some way, shape, or form.
Now, I have to wonder, like an air cylinder company, you want to sell more air cylinders, right? And I'm thinking, why would they want to show you how to put a universal joint in the end? They won't make very much money, right? Just like, and then also the linear slides, CHK, they want to sell more. So why would they give you a fix? You know what I'm talking about? So it's one of those things where you have to wonder, it's just like the door hinges. Oh my gosh, all the doors are over constrained all around the world. Maybe because they want to sell more hinges, you know what I'm talking about? And so that's why I think this tool is very powerful. You can call people's bluffs now, right? You know it, right? And so that is really neat. And then there are companies that are set up that way. I'm serious. There are companies that they want spare parts. That's what gives them business, right? You have to remember that. But obviously, designed for Universal and Disney, they won't like you doing that, right? And the funny part is when I was teaching this class to Universal, at the time they had in their requirements that never to use a trunnion joint on a cylinder. Like a cylinder body, you have these 2 pins that come out the side of the body, and they said never use those because they never work. And then as Brian and I and another member were doing our mechanisms for the animated figure, we needed to save space, so we used a trunnion. And then we proved to them through math, through Gruebler's, that hey, the trunnion we put on universal joint basically, it works fine. Trust us. And we had to get a sign off on it, and then we were allowed to use it. But then after that, now they know Gruebler's, they know all stuff now, right? So that made us feel much better, right? And then one of the things that I like to do is I love the original movie RoboCop, and you see it back there. I made the original one out of Dollar Tree foam. There's like 500 parts that are cut by hand. did it all from scratch. And then Brian introduced me to the Polulu board, and then a 3D printer, and this is why I made a 1/6 scale of that. So now there's two parallel bars, right? Sliders here, so it's over constrained. But using Gruebler'S, you have to put a universal joint here and a ball joint, and that's why it doesn't bind when it's moving. So again, Gruebler'S again.
That's super cool.
Cool. All right, any other questions? All right, well, if that's it, yeah, please, I can send you guys my calculator if you like. This is basically have a spreadsheet, right? So you just fill it in because this is what Universal is going to expect you to kind of fill out. Not this form, but something similar to this. And I'll just email this to Brian. You guys can have this, and it kind of helps you walk through how to do mechanisms. So what you can do is you make any mechanism you put, just put an image here, and just kind of start counting off how many moving parts there are, how many constraints, and it kind of gives you the answer. It's kind of like a cheat sheet, you know. And so, but I've done mechanisms. Once you use this, you can do it all by hand, you know. So if you look at my video channel, at the end, I used to just do it all by hand. Here, I'll show you right there. So you just do it all by hand. You don't need that chart, you know. But that's like, you know, when you start, you kind of need the chart. But afterwards, you can do it all by heart. Okay, that's all I have. So thank you very much for listening. I really appreciate your time and all the questions. And please feel free to have any questions. Just email me. My email is in the invite, I believe. It's called Gruebler'S Fourth Bar at gmail.com.
Thanks, Lay.
Thanks, Lay.
Great. Hey, thank you
for your
much.
time.
Thank you.
Thank you,
Have
Lay.
a great day. Okay, bye-bye.